Welcome to the course on GPU architectures and programming. In the previous lecture, we have been discussing about how matrix, the simple idea of doing matrix multiplication in using a GPU can help in optimizing. I mean, how that can be accelerated by using some GPU specific constructs like the shared memory based optimization and also using the idea of global memory coalescing. So, based on that, let us look into this example. Now, first thing we will do is we will define a notion of a tile. Essentially, a tile will be what same as the block size. So, we will be considering two dimensional blocks. So, that is why we will define the grid of that is the number of threads I am going to launch is still n square. So, that is the dimension of the matrix. But the launch parameters I will be doing a very careful selection. So, what I will do is I will define, as we have discussed, something called a tile, which is essentially equal to the block size. So, in two dimensions I will decide the size of the tile based on the size of the shared memory, and we will soon see that how that can be done. For now, let us consider that the tile size is the block size, and this is an example picture we are showing. So, the grid is defined as a collection of the 3 cross 3, that is 9 number of blocks distributed in 2 dimensions, and inside each block I have a 2-dimensional arrangement of threads in 4 cross 4. This is an example where essentially I am holding n as 12. This is of course a simplistic example. As you can see that it maps nicely with our original idea that we are considering 2-dimensional matrices. So, I will definitely consider the blocks in 2D and also the grid, I mean also inside the block, inside the block things are in 2D and the blocks are also packed in 2D, because that would give me very nice access expressions. Now, how do I figure out some specific row and some specific column for a given thread? Again, that would be quite easy. So, essentially here we are setting the block dimension in the x and y axis both equal to the tile width variable. Now, of course, I mean it will depend on the dimension of the matrix here. So, the tile width variable is going to give me the block dimension in the y direction and similarly in the x direction. So, if you just replace this with block dim dot y and this one with block dim dot x, that gives me the usual access expressions for the row and column for a specific location in the matrix, right. Now, how do I figure out that in which tile I am located? So, I want a loop to decide that which tiles to load or which tiles to access, right. So, essentially the basic principle between inside this computation is as follows, that threads computing inside a tile would do collaborative loading and computation. So, earlier in our naive algorithm, let us say any one thread, the ijth thread was bringing data from the ith row and the jth column, multiplying and accumulating them to compute the ijth location. But now we are saying that no, we will do something different. Instead of this entire tile or the corresponding block, whatever threads are there, they would do collaborative access, collaborative computation, and when all the threads computing for this block would finish, they are done with computing all the elements for this tile in the output matrix. Now, for doing that, what is the region of access required in the two input matrices? So, of course, as you can see that for a single row it would have been for a single location it would have been a single row and a single column, but for a region it would actually spread. For all the locations inside this shaded output tile, I would need access in M1 in all this entire region, right. And similarly, here I would need access in this entire region, right? But the issue is still not fixed. How am I going to do some optimization and decrease the number of loads that are going to happen in the global memory? That's the key thing we are trying to do, right? Just another point we like to make here, that suppose somehow we have figured out how to do some optimized computation of things inside this output tile, but then let's call it some method 1, some method optimized method, right? So if I am using this method, how many times I am going to call this optimized method? How do you figure out that? Earlier I was computing for each location, and that I was doing n square number of times, but now of course for calling I have to if I think that I have this, as I was discussing, that if I am using this optimized method for doing computation for one tile, the number of times I am going to call this method would be the total number of tiles here, right? So what is the total number of tiles here? Width by tile width square, right? Because as we can see in this example, that since the tile size will be divided by the width, I mean considering width and length both same here, so I have got to access that many tiles here on the x side and on the y side, you multiply them, so you have to access this many tiles, right? Now if I think that okay, for so this MOPT would be accessed this many times. Now let's try and look into the functioning of this optimized method, right? So first of all, since I have broken down the matrix into this kind of coarse grained distribution of blocks, which I am now calling them as tiles, now observe that for computing this output tile, I need a loop which should iterate through M1 and access 3 tiles, right? Because this is the region we have marked which needs to be accessed. This region can be nicely broken down into 3 tiles. As per this picture, in general, I can say that it can be nicely broken down into this width by tile width number of tiles, right? So for computing this output tile, I need to access this width by tile width number of tiles from input matrix 1, and similarly I need to access this width by tile width number of tiles from the input matrix 2, right? However, I have to figure out what is the location of each these tiles through suitable variable indices. I have to load these tiles into the memory, and then I have to do some computation, right? So I can say that all the threads which are computing for this block, the output tile, the first thing they have to do is they have to load, let's say I set the loop iterator variable m as 0, and I load the tile 1 here and the tile 1 here, and then I do some computation using them. Then I load the next tile from here and the next tile from here, I do some computation using them. Then I load the next tile from here and the next tile from here, and again I do some computation using them, and finally all these threads inside this block, they are ready with the output. So I am loading in tile sizes and I am doing some computation using the data. Then again I am loading in tile sizes, I am doing some computation using the data, and that's how I am going on. Assume that for the timing, assume that this is going to work, right? So if this idea is really going to work, then I would essentially have a sequence of load followed by compute, again load followed by compute, right? So essentially I am using a set of threads in the same block to load two tiles, right. So, I have effectively loaded this tile and this tile and did some computation with them, and in that way I am making some progress, right. So, I have loaded these two tiles and made some computation. Then again I have loaded the next tile, this one and this one, they are highlighted here, the next tile, this one and this one, and again I have done some computation. So, this picture is shown using smaller size. Let us say I am showing a, instead of having this kind of 3 cross 3 number of total tiles, in this picture for representation purpose I have 2 cross 3 number of total tiles. So, I am trying to show that suppose that method works, then essentially the threads which are doing some computation for this region, they are going to, so they are going to collaboratively load data from this tile of matrix 1 and this tile of matrix 1, do the computation. So, this is the load phase, and using the loaded data in the shared memory they will do some computation. Then again this is the next load phase. So, this is matrix 1, this is matrix 2, so they are loading the two tiles, tile 1 1, tile 1 1, they have put them into the shared memory and they did some computation. Then they are loading tile 1 2 and they are loading tile 2 1, right. Then again they are doing some computation, and with all that the final result is ready. But the question is, what is the good thing here? How does this really help? Still we are assuming that this sequence of load computes are going to work. We will see that why it works. So, suppose that works, then I would write the kernel like this. So, inside the kernel I would define two shared memory locations, each which are of the size tile width called tile width. Why? Because assuming that I am going to do this kind of load compute, I am loading these two tiles from these two different matrices, input matrices, into the shared memory, right. The compute phase will go on in the shared memory and we will see the advantage out of it, right. So, the two tiles have to be loaded by the set of threads who are working for this part of the computation. So, the set of threads are going to first load this tile from matrix 1 and this tile from matrix 2 into the shared memory. So, I define two shared memory locations, each of the size that should be able to hold two of these tiles together, right. Then I get the block IDs here and thread IDs here in these smaller space variables, and then I have to perform the actual loads, right. So, to perform the actual loads, I first figure out the row and the column index for the locations. So, essentially what does this mean? I am essentially putting in here two variables row and column, which will actually, so if you just take the example of what is what do I really get out of this block ID y and thread ID y of any thread. So, any of the threads are trying to figure out that okay, what is the location for which it is going to load. Right. So, block ID y times the tile width plus thread ID y, comma, this is block ID with respect to x. So, what is this block ID? Times the tile width. So, you come up to here and then the thread ID x, right. Why am I really multiplying the block ID with the tile width? Basically, that gives me to figure out exactly, I mean, okay. So, this is the, so if I multiply this by by tile width, I get to here, So I get to this much, and then I shift by the tile width. Similarly, with Bx times tile width, I get to this much, and then I shift with the Tx, right. So this helps me to figure out for each thread which locations of the input memory is going to access, right. So as we have discussed that all the threads who are working on this output tile they are going to bring data collaboratively from two of the input tiles, let us say this one and this one, or if we look at the simplistic picture from this tile and this tile. For first of all, they would figure out which of the locations of the thread of the input tiles they are going to access. So for that, they simply use this row column indices, and they using this row column indices, they would compute the corresponding location in the original input matrix. So essentially, as you can see, the row will get multiplied by the entire width of the matrix. So that gives me the row the position in the first row, and then I multiply with the loop iterator variable the tile width, and then I get into the tile with the Tx position. So I hope this gets clear now. So first point is, since I am going to do this inside a loop, in the first phase I am going to access things from these two locations. So for this location, essentially what are the positions that this thread are going to access. So in the first phase of the load compute, it is going to access data from here and here. So when this loop runs for its first iteration, m is 0, so row times width plus Tx. So you have already figured out the row times width, that gives you this position here, that which row, and then you shift by the Tx amount. That is the amount of shift you have here, right. I hope this is clear, because this is your Tx. So you just shift by Tx inside the first tile of the corresponding row. So in that way, the thread has figured out which data to bring from matrix 1, and similarly using the other expression, it will figure out which data to bring from matrix 2. So as we have already pointed out, those will be the exact data points that that thread will bring in. And finally, when all the threads corresponding to that tile have executed this code, what do I really have? I have this situation, that for all the threads in this tile, they have brought in these two data points from the shared memory, from the original global memory of the matrix to the shared memory, right. So now in these two tiles, I have got these two data points, right, for the threads working here. For the threads working ones for some other tile, they will be doing collaborative load from some other locations, right. So these threads have done this this part of its work, right. They have first figured out they belong to which tile, and then they have brought in data collaboratively in parallel from here and here, and then they are going to get into this loop through which they will do a partial sum computation. So what does that mean? So if you look into this picture, finally what is going to be the output for this location? Let us take any random location, the one that we are talking about. So that would require me to do an addition and a multiply add for things here and here. What am I really doing is, I am phasing this multiply add into three parts. In the first part, I load things from here and things from here and do the multiply add. In the second part of the computation, I will load things from here and things from here and then do the multiply add. In the last part of the computation, I will do this and then the multiply add and get together everything done. So when the threads which are working collaboratively here would bring in this tile and this tile. So, essentially after bringing in these two tiles in the shared memory, what they will be doing is they will be doing their part of the multiply add operations for only these parts. That means for this thread, for this thread, this was responsible for bringing data from this location and this location. But parallelly, the other threads for the other locations have brought in the data points and stored them in the shared memory, which this thread itself requires, right. So, this thread will now actually use data point brought in by other threads and do the multiplied add operations this thread is supposed to do, but up to this much, not the entire thing together. Why? Because I have not still brought in the data for the other tiles into the shared memory, right. This is the main reason. So, similarly what is happening? While this thread is doing its part of the computation for this location, all the other threads in the tile are doing their part of the computation for various other locations. For example, if I consider the thread corresponding to this point, it had brought in this data and this data, and after bringing in those data points, it is traversing this much and doing the multiply add, right. So, after all the threads for this tile have brought in this tile and this tile and then done the computation, what do I have? I have some data points computed for all the locations, but they are not the final results. They are all partially computed multiply adds for corresponding rows and columns. But what was the good thing here? The threads were actually using data brought in by other threads in parallel, right. So, all the threads in this tile have brought in data and stored them in the shared memory, and now while doing the multiplied operations, they are accessing data from the shared memory, and they are not only accessing data that they have brought in, they are also accessing data that other threads have collaboratively brought in. So, with this, if I progress with the code, so first of all, after ensuring that all the threads have brought in the respective tiles in the load phase, then only I should go into the compute phase and do the partial sum computation. That is why after bringing the data, there is a sync thread, and then as long as I am not done with the partial sum computation, I should not go into the outer loop and bring in more tiles, right. So, that is why until and unless the partial sum computations are already done for whatever data was brought in the previous load phase, all the threads need to synchronize. Only after this point, what is the guarantee I have? The guarantee that I have is this is right now having partial sums computed considering 2 of the input tiles. So, once all those threads synchronize there, they will again revert back to the load phase. After reverting back to the load phase, so assuming that this have already been taken care of, these input tiles have already been taken care of, these threads would again bring in more tiles through the load phase and again start doing the computation. So, that is what is happening here, right. So, again they will go in here, bring in data in the shared memory, again have a sync thread when all the data points are ready, and then they will again do parallelly collaborate into doing the computation for the multiply add. So, for this simple example, it is getting done right here, right. So, since I have only 2 cross 2 number of tiles, so essentially the threads which are responsible for doing computation for this 1,1 position tile, it will have 2 load compute phases. It will load tiles from here and here into the shared memory, then collaboratively compute the sum. Again in the next phase, it will load the other 2 tiles and collaboratively compute the sum, right. In general, it will be having much more number of load and compute phases like that. So, overall, as you can see that only when the entire sequence of loads and computes are done, the partial sums will finally get an update and they will represent the final result. right. So, once each thread has completed its sequence of loads and computes, the corresponding its own private copy. So, this is the private variable, right, for each thread. It would have the final value corresponding to its own ijth location, right. So, then it would actually load this final value in the corresponding location in the target output matrix in the device memory, right. So, this dp is the target output matrix in the device memory. It is getting updated only at the last. So, to make things much more clear, what is happening is, for doing the computation of this tile, threads for these locations are making progress in parallel. First thing they did is, all the threads together brought in stuff from these two tiles, and then they made progress. For example, this thread made progress like this, and this in parallel some other thread was making progress like this, and again in the same column like that. But after this phase is done, all the threads have covered all these positions, right. See, everything is still going on in parallel, like our original unoptimized CUDA kernel for parallel matrix multiplication, right. Like, while this thread is been computing for this tile, the other threads are of course computing for their respective tiles, right. But the good thing that is happening is, each thread is not performing all the loads it is required to perform from the global memory. That means each thread is not bringing the same row of data multiple times. This thread has brought in this data, whereas the next thread has brought in the next position of the data. But for doing the computation, this thread is using all those data, loading them when it is requiring them from the shared memory, not from the global memory, and that means many number of global memory loads are getting changed to shared memory loads. As an example, I would just again revisit this. So, consider the threads who are working here. So, essentially, if I consider all the data that is brought in by these 4 threads, it would be this, whereas the other threads are bringing in data for other locations. But when these threads are into the compute phase, for example, the first thread is accessing everything from here and here, where all these other entries have been brought in by threads of these locations. But when this thread is doing the compute and loading data from these other locations, it is doing all these loads from the shared memory. It is not doing these loads from the global memory. That is the most important point. So, essentially, once all the actual global loads have been performed while bringing the things for this entire tile collaboratively by all the threads in parallel, after that, in the next sequence of multiply and add operations inside the inner loop, all the operations are now shared memory operations. So, I can now say that, okay, I have a clear difference here. All these loads, these are my global memory loads. But after that, all the threads are accessing data from the shared memory. So, all these accesses are going to be shared memory operations. And those global memory loads, what is the good thing about them? So, here I come to the next part, the next fascinating part. So, observe the load pattern. So, when all the threads are loading data here, so I am loading data from all these places, right. So, all these loads will be coalesced, again all the other loads will be coalesced, and like that, right. Similarly here, since I have broken down the computation to these phases of loads followed by compute, again loads followed by compute. So, these loads are now nicely coalesced. So, overall if I am trying to do a computation of how many memory accesses are done for computing a tile, so it is equal to the number of memory accesses you require to load a tile times the number of tiles to load from the two input matrices, let us call them A and B. So, what is the number of tiles to load? So, if you think, so this is for computing a single tile, right. So, the number of tiles to load would be, so this is n, you divide it by the width, so that gives you n by w number of tiles here and similarly here. So, total you have got 2n by w number of tiles to load for computing in a single tile. So, you have got in total these many tiles to load, and what are the number of memory accesses required to load a tile? Well, as we have discussed that when I look into the tile, all these accesses are going to be coalesced row wise. So, the number of accesses would be w by 32 times w. The times w would come for each of the different columns, but in each of the row I have got coalescing w by 32. So, this is the total number of accesses for computing a single tile. The total number of memory accesses in general would be the total number of memory accesses for computing a single tile times the number of tiles. So, that would give me w by 32 times w times 2n by w times the number of tiles is of course n by w whole square or n square by w square. So, that gives me n cube by 16 w. So, that would mean if I can choose a w which is significantly big, I can have an order of magnitude reduction here by n. So, if w is comparable to n, it's some big fraction of n, I can have lots of acceleration here, right. So, that is the primary takeaway of message here, that with significant amount of tiling, depending on of course the amount of shared memory you have available, I can reduce the total number of global memory accesses for computing this matrix multiplication by a significant factor by getting the threads to collaboratively work from the shared memory, and also the tiling is helping me to increase the amount of coalescing that is possible here. So, in that way it leads to significant number reduction in the total computation time, and as we know that matrix multiplication being a fundamental operation, being many part of many large many significant optimization techniques and ML workloads and many other places. If you can accelerate matrix multiplication, that really helps in so many application domains. So, this is one of the most fundamental computations where GPUs really help, and we will take several such examples of other computations in the next lecture. Thank you for now.